optimizing to a product of sums with Karnaugh maps. Karnaugh map optimization is used to develop a two-level network that is optimized as much as possible. So what you do with a Karnaugh map is you take a truth table as input, and then you find an optimized sum of products Boolean expression based on that. The circuit consists of an array of AND gates that then feed to an array of OR gates. So the input variables may or may not be inverted. And the reason for saying it's a two-level network is we have this array of ANDs here and an array of ORs. Here we have just one output variable, so there's only one OR gate in the array, but if we have multiple OR gates, then we could have multiple outputs. The product of sums optimization is used to develop a different kind of two-level network where we have OR gates feeding to an AND gate. So this is what we call a product of sums implementation. And it differs from the sum of products implementation where we have the AND gates feeding to OR gates. So AND gates feeding to the OR gates, like so. So if we want to develop a product of, or sum of products expression, we could just use a K-map. Starting with this Boolean expression, we have f equals AB ended with C prime or BC or A prime, and then that larger term ORed with C prime ended with A prime or B. Let's develop a truth table and then optimize it using a K-map. So f equals AB C prime or AB BC or A prime B. This covers this part. And then we OR with A prime C prime or BC prime. And we've now covered this term as well. Let's optimize a little bit. So we get ABC prime, or you can use it in potency here, ABC, or A prime B. This goes to 0. ORed with A prime C prime or BC prime. We now have a Boolean expression that is a sum of products. Let's develop the Karnaugh map to optimize this sum of products expression. A, B, C, and here is the K-map we're developing. 0, 0, 0, 1, 1, 1, 1, 0. Then A can be 0 or 1. Let's fill this in. A, B, C prime, A, B, C prime, A, B, C, A, B, C, A prime, C prime, A prime, C prime, A prime, C prime, B, C prime, and then we have B, C prime. So BC prime is here. Now we can optimize. 0, 0, 0, 0. Let's find our groups. An optimal set of groups would be here and here. F is equal to A prime C prime or A B. and we have our Boolean expression. This then could feed to a set of AND gates. So we have, let's just draw out our variables A prime. We'll assume that these are given. B prime, C prime. We have two AND gates, A prime and C prime, then A ANDed with B, and these feed to an OR gate, or an output F. The product of sums procedure is a little more complicated than just using K-map. First, we have to obtain a sum of products for F prime using the remaining minterms. Then we need to complement F prime to obtain F. And we need to apply De Morgan's rule to all the sums and products. And this will give us our product of sums. So let's go through an example of this procedure. This is the same as the previous example. We have AB, C prime, BC, or A prime, ORed with C prime and the quantity A prime or B. Let's say we have F prime instead. This is going to be equal to AB ANDed with C prime or BC or A prime, ORed with C prime ANDed with A prime or B. And this is quantity prime. Notice I just copied F. Now we can use De Morgan's law to distribute this prime. This is equal to AB ANDed with C prime or BC or A prime, quantity prime. This is ANDed with C prime and A prime or B, quantity prime. Notice that this OR symbol turned to an AND because we distributed the inversion to these two terms. Now we can distribute the inversion further. Equals A prime or B prime ORed with C prime or B, C, or A prime. This is ANDed with C or A, B prime. So we distributed this prime into this term here, and we got C or AB prime. So we can simplify a little bit more by distributing into here. Equals A prime or B prime or C ANDed with B prime or C prime ANDed with A. And then we AND this with C or A, B prime. So we need to take this expression here and find the sum of products for f prime. Remember, this is f prime. So let's reduce this to a sum of products. So we have a prime or b prime or a b prime c or a c c prime. This is ANDed with c or a b prime. Notice that because we have b prime, this can drop, and this goes to 0. So we have a prime or b prime here. We have c or a b prime here. Now we can use the distributive property. A prime c or a prime b prime. So I distributed this term to here. Now we're going to distribute the b prime term, b prime c or a b prime b prime. Idempotency, and this drops to 0. So we have a prime c or b prime c or a b prime. Let's create a K-map for f prime. A b c So we'll count with gray code counting. 1, 0, 0, 0, 1, 1, 1, 1, 0. A is 0, A is 1 for the rows here. A prime C. So when C is 1 and A is 0, we have a 1 and a 1 and a 1 here. B prime is 0, B is 0 and C is 1, so B prime C. So here and the other is filled in right here. And then we have A, B prime. A and B is 0, A is 1, B is 0. The other's filled in, and then the remaining entries are zeros. This is for f prime, remember. Let's find the groups. Minimal sum of products form for f prime. F prime equals, the first group is A prime C, ORed with the second group, A B prime. Notice this is for f prime. We want f for the sum, product of sums now. So we find f by saying we take the inversion of this sum of products form. Distribute by De Morgan's law. F equals A or C prime ANDed with A prime or B. So we have a second expression here for f, which is a product of sums form. Let's try now simulating this. So what we're going to do let's take our f expression and and we'll bring it here to our simulator. This is for the product of sums form. Let's bring our sum of products form, which is here, to our simulator as well. And let's verify that these two expressions are the same. So what do we need? Well, we have three variables. Let's draw them. A, B, C, A prime, B prime, C prime. And now we need our inversions. So we bring out our three NOT gates. And then we can label A, B, and C. So let's implement the sum of products expression first, this one. F equals A prime, C prime, or AB. Two AND gates. A prime, C prime, to A, and then to B. And these two AND gates feed to an OR gate. Now let's implement the product of sums version for F here. These should be the same. A or C prime, so let's pull out an OR gate again. A or C prime, A prime or B, and these two are ANDed together. We have A ORed with C prime. We have A prime ORed with B. Now we'll bring out our binary probe and probe both of these outputs. We're getting X's, so we need binary switches for A, B, and C. Let's label these so that we have a virtual connection. We're using LogicWorks, the LogicWorks simulator in this video, but you can use other simulators to test these circuits and verify that they are correct. So let's go through. The output of the sum of products form should be the same as the product of sums. Let's just go ahead and label these here. SOP, and then POS. And we will move these appropriately. All right, Let's go through all possible values of A, B, and C. So we have 0, 0, 0. Watch these two values here to make sure that they stay the same. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. It's the same. 1, 0, 1, 1, 1, 0, and 1, 1, 1. And notice that even though we have two different circuits, we have our sum of products form and our product of sums form in their different circuits, we still get the same value. One small note in this video, I discounted the inverters in the final counts of the number of gates. The B inverter is not necessary because, as you'll note, we don't connect to any of these logic gates here on the first stage or the second stage, so this inverter is unnecessary. The reason I placed it in, though, is that sometimes we get both the original variable and the inversion, as we will see when we go to sequential circuits.